Recording. So I'm in a presentation and we're gonna go over some code, but the way we're gonna do this is uh, we're gonna have the opportunity to ask questions at the end of each slide, just because there's not too many to get through and there's a lot of information on each. So to start with, we're making a rootkit for pfSense, which runs on the FreeBSD kernel. We're coding this in the C language, which on the next slide I'll say why. But an important part of how the C language is a little bit different than other languages is a primitive type called a pointer. So what a pointer is a variable that holds the memory address of another variable. So what that means is when you execute any code, any program, you have variables, just like in Java and Python, but those variables are stored in memory, and higher level languages take care of accessing and changing those values for you. But in a lower level language like C, you have to access that memory in order to change those variables yourself. So a pointer holds the memory address of a variable. So for instance, if we're looking up here, you have a main function and you declare an integer a, and you can assign it whatever value you want. But then we have an integer pointer p. So this little star declares that p is a pointer, and then int is that it's pointing to the type of an integer. If we then set a equal to 20, then the memory address of a now holds the value 20 as an integer, but you need to access the memory address of that variable in order to call it. So p is going to be holding the memory address of a, and this ampersand right here is declaring is dereferencing. So what that means is it's accessing the value at that memory address, right? So if you example said print a, all it would do is it would print a whole bunch of jargon like aux00ff whatever, because it would give you the memory address of a and not the actual value in there. So this ampersand is dereferencing, which means that it's going into that memory address and actually grabbing that value. Structures. In C we have, or in Python, you have classes, and you can think of a structure as pretty much a class. They're very similar. They just group different data types together, and it just makes it easier to reference things. So super simple example, type def is defining the type of the structure. And you say struct student. So we're defining a structure named student that holds these different variables, right? So you have a character pointer to name, you have an integer age, double GPA, and then a car is CS major. The main point here is that it lets you hold a bunch of different values all in the same structure and reference it easily. The C language. Why are we using C? So the other option is pretty much Rust, which we would have preferred to use. At least like that was the general consensus. Because it's just like a little bit easier to code from what I've heard. Not that any of us, or not any of us, but not that I've tried it yet. But we actually cannot compile Rust in the environment that we need. So we have to use C just because of the way that the kernel works. So I'll get into this in a little bit, but we're making something called a loadable kernel module, which is a piece of compiled code that just tells the kernel to add functionality without needing to recompile the entire kernel. So we need to use the C language, and Rust was unfortunately not an option. Does anybody have any questions up to this point? Nope. Okay. Continuing. Compilation. So C is a language that needs to be compiled, and there are a couple of different compilers that you can use for C, but for our case, we need to use LLVM 15.0 because that's the only compatible type with the weird ass kernel version that pfSense is using. So if you're looking at this image down here, uname tag A just gives you some relevant information about the kernel version. So this is pfSense 2.7.2, which is our target operating system. And we can see that the kernel version that's getting ran is 14.0 current FreeBSD. So what current means is that when a kernel or an operating system is in development, Git pushes are still happening, right? Like there's changes that are happening on the fly. And until that version is done, it is known as current. And once that version is complete, it moves on to something called a stable version, which just means that there's not going to be any more major modifications to that operating system or kernel. Why this is important is that we are past version 14.0 of the FreeBSD kernel, meaning that the only kind of 14.0 FreeBSD machines or kernels that you can actually get are the 14.0 stable versions. I've tried messing around with the stable version to compile within those and then loading them within pfSense, but it didn't work, which means that whatever current version that pfSense is running has some different kernel functionality than the stable release. What that means, unfortunately, is in order to compile code, we need to turn pfSense 2.7.2 into an environment in which we can compile in. I have managed to do this and made a working LKM, loadable kernel module, so we can compile, which is good news. And I also made documentation on how to make that environment in case anybody else wants to compile and test themselves. So really quick, I'm going to go over what an LKM is. So an LKM is a loadable kernel module. So what that means is you have the kernel, which is the core of the operating system. It's what manages basically process requests to use hardware. So like when you run YouTube is going to need to use some resources to go and load things into memory and actually display things for you. So when you boot up your system, every time that you do like a full reboot, your kernel actually gets recompiled. So, So your kernel gets recompiled, but what that means is for our functionality, if we wanted to change something within the kernel itself, we would need to shut down the machine and then recompile it. And from a red team perspective, this is not good practice because, if someone's on a box and then they see their box randomly like restart and then it does some weird stuff after, then probably you're going to be suspicious and they're going to go thrunting. We don't want people to do that. Luckily, there is a different implementation for kernels, which is something called loadable kernel modules. What these are dynamically available modules that you can plug into the kernel without needing to recompile it. So what that means is the kernel has its own set of actions based on its functions that it executes, but you can load a module that the kernel will then use as additional functionality before returning anything, and it doesn't need to be recompiled. So that's why the Rootkit that we're making is a loadable kernel module, which just means that we compile it to be a certain structure that is called a kernel module, and then we have to load that rather than recompiling. So that takes care of what an LKM is. So this structure here is the main part of the Rootkit, like what we're actually trying to do, like how we're taking advantage of malicious executions. So within the kernel, there is something called the system sent table, which is just a structure that holds different syscalls. So a syscall is what happens when a program asks the kernel to do something, right? So when a program asks the kernel, hey, simple example I can think of, if you have a Python program that says add 2 + 2 and return it, it's going to have to go to the kernel and say, hey, can I use some resources to add 2 and 2 and then return that value? And the kernel is then going to go to the syscent table, and based on the arguments passed in, it's going to call the correct call and then act on that itself to do calculations and then return. So the reason this is important for us is because what we're going to do is we're going to basically take out these original system calls and then replace them with our own malicious system calls. And I'm going to show code in a minute so everyone can actually see what that really means. But it's just messing around with memory addresses and adding additional functionality. Any questions? Okay, moving on. How do things make kernel calls? So a kernel call is the same thing as a system call, right? When a program wants to commit or execute functionality with the hardware, it needs to make a kernel call. So the way that actually works is not awfully complicated, but it's a little bit weird. So the example I always go back to is in Linux, if you run the ls command, it's going to go to the libc wrapper, which is the standard C library within Linux. And it's going to say, hey, I need to use the functionality of the wrapper called read. And read is just a wrapper for the system call sysread. Sysread is what actually the kernel catches and then does its executions on. And read is what takes care of actually calling the sysread and just returning values and making everything flow smooth. So your user program, for example, ls, is going to call a C library wrapper. In our case, is going to be read instead of write. And then that wrapper is going to call the system call, in our case, sysread. And then the kernel is going to catch that sysread was invoked, execute operations, and then it's going to return back up on the chain. So that's how things actually make kernel calls. What is a kernel call? This is where I'm going to get into a lot of detail because it's kind of complicated, and this is the actual functionality of the code we're going to write. So I'm going to stop again real quick and ask if anybody has any questions.
I'm sure I will after this. Let's take a look.
Okay. So, again, for now, all that we're going to try to do is we're going to try and make ls have malicious functionality. So the first part of our program is we're just going to try and hide a certain file from returning an ls. For example, let's call it malware.exe. So if we're in a directory and we have a file called malware.exe, we want it so that when somebody runs the ls command with tech-l or tech-a, either way, they will never see the return value malware.exe. However, we need it to still work, right? So if malware.exe is RC2, for example, or just other malicious implementations or things we don't want people to see, then we need other functionality to still work. The reason that's important is because ls is not the only program that makes the system call sysread. Anything that needs to locate a file is going to make that call of sysread. What that means is we can't just make our handler like a little bit different. We're going to need to check and make sure that ls was the original process that invoked sysread. Fortunately, this is not super hard to do, since whenever you invoke a command within Linux, metadata gets loaded into CPU registers, and we can just read those to figure out if ls was what's committing or executing, right? What actually made the sysread call. So that's part one, right? We need to check and make sure that ls actually committed the system call of sysread. Number two is we need to make our own custom handler. So a handler is just a fancy name for a function that does something when it's invoked, right? Like when it catches something. So sysread has its own code, right? And it's a handler. What that means is that it gets invoked, and then the kernel has a handler that's basically like, oh, sysread just got called. Let me go and do that functionality. So what happens is within the sysend table, sysread is actually just a memory address. So the sysend table is just an array of pointers. So it just has a whole bunch of different pointers to the memory addresses of different functions. What's super cool about this is that the sysend table is a global variable, which means we can just go and grab those memory addresses, and we can also change them with a kernel module without needing to recompile. So what's super easy to do is if we make a custom function to basically replace sysread, we can just go into the sysend table and replace the memory address of the original sysread with our malicious sysread. And that's what we're going to do. So this is super easy to do. It's literally 3 lines. First, just store the memory address of the original sysread. Number 2 is to then put the malicious handler in place of the original sysread. And then 3 is to have the handler invoke the original sysread. Because otherwise, we would need to rewrite all of those different kernel calls, which would be a pain in the ass. But we can actually just invoke the originals and then commit our functionality. And as long as we do that before our custom handler returns, then the kernel will not basically override that malicious functionality. So now I have to get into how these actually work on a little bit of a deeper scale. So what actually happens when you invoke any system call, and again, we'll just use sysread here for example, is before anything gets invoked, the CPU is in user mode, which means that it doesn't have permissions to screw up your computer. So you invoke sysread, and then your wrapper read, right? That's the libc wrapper, is going to go and create a buffer. And a buffer is just some memory that's used for a short time, just like as temporary storage, essentially. So when you call ls, the first thing it's going to do is it's going to make a buffer, and then it's going to store some metadata. And that metadata is just saying what it wants and the amount of bytes that it can accept back. Then it's going to call sysread, and the kernel is going to call the system, is going to catch the system call. Then the kernel goes, ooh, it's my turn, and it's going to switch the CPU into kernel mode, which means that now it's time for the kernel to execute things. Now, the kernel makes its own separate buffer. Then the kernel goes and it reads all the files in the directory, and it puts all of that data into its buffer, into the kernel buffer. Along with this, there's going to be a return value from sysread. That return value is how many bytes of data were actually put into that kernel buffer. Then the kernel will say, it's basically a checksum, right? It's then going to take that number and load it into a register. And then what it does is it copies the information from the kernel buffer back into the user space buffer. Now the kernel is done, and it's going to hand control the CPU back to user mode. And then the libc wrapper goes into that buffer, grabs that data, goes into the CPU to find that number of bytes. And if those match, everything worked perfectly, and then it'll print and return your ls values. So our functionality is that within the user space buffer, we are going to essentially just regex for values and return them. So for example, if we have a file called malware.exe along with our other files, the kernel is going to make a buffer, and it's going to put all those files into its buffer. Then it's going to copy everything into the user space buffer, including malware.exe. Now, before sysread actually returns and everything goes back to user mode, we have a chance, if we use a custom handler, to regex for malware.exe and just remove it from the buffer. The other part of that is that we now have to go into the CPU registers and modify the return value of sysread, which is possible because we're still in kernel mode. So we have to modify that value to match the number of bytes of the new buffer, right? Because we actually changed the number of bytes that were in there so that they match. And then our custom handler is done, and it will ship everything back up, and ls will return everything except malware.exe, even though it's still there. Okay, that was a lot. Questions? None?
I thought it was interesting how, so you talked about how a lot of different, I guess, shell commands will use different syscalls. For example, what was it, like the read function, the read call?
Yep.
That ls uses. Is there a benefit, I guess, to making our malicious code only activate on certain commands like ls, or would it be better just to do it on the syscall itself?
So the benefit is that we only want malicious like handlers to work in certain use cases, right? So when you call vim, for example, if you want to modify a file, that also uses the read command. So it's going to also make the exact same system call to grab the files, and then it's going to do essentially its own regex to see if that file exists. If that file does exist, then it'll go and make another syscall to grab all the contents. But if it doesn't, it'll automatically create a new file, right? So we need to make sure that our custom handler, again, for this example, just for ls, is working only for ls and not for things like vim. Because if we have malware in there that, other people on red team need to go in and change via vim, they won't be able to, because it'll just make a new file. And then that could also mess up a lot of things down the line if there's multiple files actually within the same directory with the exact same name.
I understand it now. Thank you.
Yeah. Anybody else? Okay, let's go over the code. So what we've done so far is not very much. What I do want to point attention to real quick is I went ahead and pushed a working version. I say working, but a version of the rootkit to main so that we can actually look at. And all that it does is, number one, is these are headers, which this is the same as an import statement in Python. It's just to include these different files, which just hold the different structures that we need to use. So all that it does is it first makes a pointer to the system call table, and then it attempts to find the system call table. It just tries to set, since it's a global variable, it tries to set our pointer to the memory address, the first memory address of the actual table. And then if it finds it, it prints, we found it. And if it doesn't, it prints, we didn't find it. This structure is how rootkits actually work, which I'll go into when I show our current version. And then this is how rootkits are displayed to users. And then also real quick, a make file is just something in C that makes compiling the rootkit a little bit easier. These are just instructions for the compiler about what it needs to do with this file. So if everybody remembers when I showed everybody like a picture and I was like, holy shit, we did it. And it was just like, you found a memory address at this random like bullshit. That's what this did. It just attempted to find the starting memory address of the system call table, which worked, which is awesome because everything is turning up buttery smooth. So for the current version of what we have right now, we have the same import statements, and then the same thing here. And again, we're starting with ls, but the reason we're doing that is because Once we finish making the custom handler for ls, the rest of them are just copy paste, like literally about 100 times, and then just modify them a little bit. So this is going to be the handler that actually like does the malicious thing. And then this is a function that just attempts to find the memory address specifically of the sysread system call. So before it just did the first memory address. This is trying to find the exact memory address we need. And then it stores it, and then it checks for it. And then this function changes the memory address, right? So right here, sysread equals custom sysread. All that this does is it changes the memory address of the original sysread to the memory address of what our custom handler will be. And our custom handler will just invoke the original sysread and then implement the other functionality, which is regexing for stuff, making sure that ls is actually what invoked, and then if we did regex and remove anything, then modifying the return value in the registers. But that's all code that we're going to get to. We have to actually make that. This is from one of those import statements up here. I'm pretty sure it's from these two. I don't know which one, but it's from one of them. This is the structure that actually declares a rootkit, or not a rootkit, sorry, that actually declares a loadable kernel module. So a kernel module needs to have basically just return cases. So all that it does is it returns a value of it was successfully loaded or not. So 0 indicates, which is kind of weird here, right? Because typically 1 is true. But 0 indicates that it was successfully loaded, and any other number indicates a different error code, essentially. So if you go, this is on any Linux machine, by the way. If you type in FreeBSD, it's KLD load. You can write KLD load and then your compiled binary if it's a kernel module, and then it'll just throw that into the list of kernel modules and then start implementing that functionality. So this is a function that just takes care of that, and it does different things based on different cases. So case 1 is when the module is loaded, we, for now, again, this needs modifications, we just find the system call table, and then if we found it, because 0 indicates that we did, then no error, and it just prints that. Otherwise, we didn't find it, and then break. And then case mod unload, because the same way that you can run KLD load, you can run KLD unload to unload kernel modules. Right now, we have nothing here, but what we'll actually do is we'll implement a persistence case, and we'll do that for a couple of other things too. And then this is just an error in case something weird happens, like a forceful power off. This function is pretty much the same as the functionality of this. It's just declaring to the kernel what the metadata of it is. So when we actually load it, and then you say list all your kernel modules, you'll see that the name of it is Rootkit, because that's kind of hard to miss. And the event handler, which is just this function, is named Rootkit handler, and we have no other data right now. And then declare module, this is some metadata that we can mess around with. We most likely won't, though. That just tells the kernel how important the module actually is. Because if you have a whole bunch of different modules loaded, the kernel has to know which ones it has to run through first, and using what hardware. Any questions? Okay, good. That's what we've done.
The code.
What was that?
After messaging you, we can't see the code.
Oh, could you not see VS Code?
Correct.
What did you guys see just now then?
Slideshow.
Just a slideshow.
Oh, what an oversight. I'm gonna redo that real quick then. Oh, what a blunder. I'm so sorry about that, guys. Do you guys see the GitHub version though?
For the first part of it, yeah, we could see it, but I think when you switch to the second part,
Yep.
for
Okay.
VS Code, we couldn't see that.
I am so sorry about that, guys. I'm going to run through this real quick again then. This is on the GitHub if anybody wants to go through it, and I have some notes that just basically say all of what I just said. But makefile is the same. The rootkit, you have your imports. This structure is the same. This is just a pointer. This is going to be our custom handler that we put in place of the original syscall, sysread. This function attempts to find the memory address of sysread, and then it prints out whether it did or not. This function then tries to change the memory address to our custom handler, which hasn't been written yet, but it just changes the memory address of the original sysread into the memory address of wherever our custom handler will be. This is a structure along with this that the kernel needs in order to understand what we're trying to load and what to do in case A, the module gets loaded, B, in case the module gets unloaded, and C, in case there is an error or a forceful power off or something happens that was not just it being loaded or unloaded. So in the case that we load our module, we have to change this up a little bit, but what we have right now is just that it's going to attempt to find the memory address of the syscent table, and then it's going to print that out. And then this is metadata regarding the rootkit. So this is what a user will be able to see when we actually load it. And then this is the line that I was just talking about, declaring how important the module is and what hardware to use it for. Again, I'm very sorry about that. I know that was super speedy. If anybody has any questions, like after the fact, of course, then please do shoot me a DM. I'm doing my best, but I realize that some of this is like really weird information that we're probably never going to use anywhere else. So moving forward, what we want to do is we want to write the code. So I'm going to do my best to find resources regarding like the actual use cases of stuff. Like, for example, like a resource that actually talks about how those buffers work, maybe in a little bit more detail. But for the most part, what it comes down to is writing this first handler. Because once this one is done, then everything else becomes super easy because it's just copy, paste, and tweak a little bit. So, right, number one is we need to check if ls is what invoked this sysread or like this system call. And if it wasn't, then we call sysread normally and we just return it. If it turns out that ls was what invoked sysread, then we implement our additional functionality, which is going to be checking if the current directory has a file name that we want to remove. If it doesn't, then again, we're just going to return normally. And if it does have a file name we want to remove, then we're just going to regex for that value and remove it from that buffer. And then we're also going to go into CPU registers and then modify the return value of the number of bytes by however many bytes the file name, the file names were. And that's kind of it for this one, which the pseudocode seems not too bad, but is going to get, the actual code is going to be kind of complicated. So moving forward, I definitely like to have everybody be more involved. And it is my fault that people haven't been more involved because I haven't given anybody resources or explained what we're doing, which is why this is kind of the start. But what I've done is kind of the hard part, which is figuring out if we can do it. And the answer is yes, absolutely we can. We can make a rootkit. We can make it do everything we want. And we have now figured out how. So if people could maybe DM me what they're interested in, or just like if they want to work and when they're available, then I can hop in one-on-one calls with people to work on it. And I'll do my best to get whatever resources anybody needs, like together to work on stuff. Because that's kind of my job at the end of the day. It's to get you guys whatever you need in order to be able to contribute to the project. Any final questions? Seems like we're good. Was everybody able to see all the code and see the slideshow?
Yep.
Okay, perfect. I'm going to stop recording here then.